Stacks and queues. Alright, stacks and queues are two more examples of container objects. Container objects are objects whose purpose it is to store multiple objects. We've already discussed two of them, array lists and linked lists. However, what separates an array list and a linked list from a stack and a queue is that an array list does not care about the order in which you add objects to it. An array list does not care about the order in which you remove objects from it. Their job is simply to store the objects and nothing more. With stacks and queues, they work much differently. Now, the way stacks operate is very analogous to how cafeteria trays operate. Anytime you add a cafeteria to a stack of trays, you don't put it on the bottom, you add it to the top of the stack, right? Then, when it becomes time to take a cafeteria tray, you don't take from the bottom, you take it from the top. This form of programming is called last in, first out programming because the last object that gets added to the container is always the first object to leave it. Now, the basic operations of a stack include the push method, which simply means push an object on top of the stack. Then you have the peek method, which simply means let me know which value is currently on top of the stack. Peek does not change the stack, it only lets you know who's currently on top. Then you have the pop method, which simply removes the object that's currently at the top of the stack. Then you have queues, which operate like a single file line. The reason I call it a single file line is because queues use first in, first out programming, which means the first object to enter a queue is always the first one to leave. The last object to enter is always the last one to leave. Now, the methods for a queue include enqueue method, which simply means add an object to the back of the queue. Then you have the dequeue method, which simply means remove the object that's currently at the front of the queue. Then thirdly, you have the peek method, which simply lets you know which object is currently on top of the queue. It does not modify the queue, it does not change it, it merely lets you know who's currently on top. So, for this week's project, there will be 4 parts. Part 1, you will create a new class named linkStack, which will operate just like a stack, and will use the myDoublyLinkedList class you created in the last project to store its values. The methods this class must have are the peek, pop, push, isEmpty, and size method. Then for part 2, you will create a linkedQueue class, which will operate just like a queue, and will use your myDoublyLinkedList class that you created in the last project to store the values. The linked queue will have the following methods: peek, enqueue, dequeue, isEmpty, and size. Then for part 3, you will create a third class named ArrayStack, which will also operate like a stack and will have the same methods as your linked stack from part 1, but will use an array to store its values. And it must be an array. You cannot use an array list. Then for the fourth part, you will create a class named ArrayQueue, which will also operate like a queue and will use the same methods as your linked queue from part 2, but will use an array to store the values. This project will be due next Monday, October 8th, submitted to Google Classroom. Now, about parts 3 and 4. So in order to effectively do parts 3 and 4, you will need to implement a programming concept called dynamic arrays, which is simply the illusion that your array is growing and shrinking. Now, why do I use the word illusion? Well, because we all know that arrays are not capable of changing size. Once you declare an array of a certain size, you cannot increase it or decrease it. And this is a weakness if you're trying to implement a class like ArrayList, for example, because your array, your static array, is always either going to be too small or too big. If you declare that each array list will have an array of size 50, for example, well, there might be an application out there where you need more than 50 values. You might need 100 or 100,000. That being said, if you decide that, all right, each array list will have an array of size 100,000, well, not every application will require that many objects. Some will only require a small fraction of that, which in that case, you'll be wasting a ton of memory. So the most optimal solution is to implement the dynamic array concept, which will allow you to grow and shrink your array as necessary. And here's how it's done. What you do once you declare an array list or a queue or a stack, whatever it is that you're implementing, start off with an arbitrary number start off with an array of an arbitrary size. We'll say for now 5, right? So you start off with an array of size 5. Then you proceed to add values to that array until the array becomes full. Once your array reaches full capacity, when you start the next add operation, you will declare a new array twice the size of the original. You will copy all the values from the old array to this new array. Then you'll add the next value. And then once the method goes out of scope, the old array will be destroyed and returned back to memory. Right? Now, because of this concept, because of the fact that we're having to keep track of not only the number of values, but how large our array is, objects that implement the dynamic array concept not only have an int that tracks the size, but they also have an integer that tracks the capacity of the array, the total size of the array, so that you can keep track of when it's time to grow your array.